Hey all, thanks for showing up. We're just waiting on some people to show up. Right now they're out there getting food, so just bear with us. We'll be starting by like 5:45. In the meantime, as always, get to know the people at your table. We've set this room up like to make it incredibly networking ready and like collaborative. So cool. Yeah, 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 yeah. Union. Okay, okay. Trend Black को call करो. All right. Hey everyone, thank you so much for coming to our Intro to Data Structures and Algorithms plus Resume Review workshop. And thanks to all of them who are watching online. Welcome to this session. So me and Trent Black and I were going to be presenting today for this session. I'll be going over just the basic stuff, big O notation, and data structures, and just some basic algorithms to go with it. But Trent Black's going to be doing some more of the problem-solving bit. So let's just dive right into it. So to start, what are data structures and algorithms? Well, data structures are a way of organizing and storing data in a computer program so that they can be accessed and manipulated efficiently. So you have arrays, graphs, trees, linked lists, etc. Algorithms are kind of step-by-step procedures or instructions for solving a particular problem. So for example, sorting, searching within those lists. So for example, you want to find if there is something in a list, you would use an efficient searching algorithm. Or if you want to sort an array efficiently, you're going to use a good sorting algorithm. So, well, how do you solve a problem? Well, choose the best data structure to represent something, apply the most efficient algorithms on that data structure. It's kind of that simple, but Trent Black's going to show an alternative approach to that too, and we're going to get into that in a bit. So just basics on data structures. We've got array, linked list, stack, queue, tree, graph, hash table, heap, try, and set. We're going to be going over some of them today, not all of them, and how they're used. So is everyone familiar with all of these, or any questions?
What is a try?
So a try is kind of like a tree, but it's used for strings. I'm not fully sure of what it is, but
It's like basically like a tree, but every node represents an alphabet of the
yeah, so it's more optimized for strings. So every node represents an alphabet. Is that right? And for all those data structures, you have different types of algorithms. So this next slide is a little messy, but there you go. So for arrays, you have linear search, binary search, bubble sort, insertion sort, selection sort, all sorts of sorts. Stack, for stack, you have different operations such as pushing onto the stack, popping from the stack, the top element on the stack. Trees, hash tables, they have their own function as an example. For trees, well, you would use that for representing, I can't think of an example right now, but the best one is hash tables. If you want to optimize for different types of searching, for example, if you want to search in O of 1. And I'm going to get into big O notation in a bit. So let's go over them. So arrays, again, are just a list. Oh, I'm just going to finish this slide in 2 minutes, yeah. Arrays are just a list, 1, 2, 3, 4, 5, 6, or the shopping list that your mom would give you. But question is, what's the fastest way to sort or search this list? Well, you've got searching algorithms such as linear search or binary search. And you've got sorting algorithms such as bubble sort, insertion sort, selection sort, merge sort, quick sort. And they work all differently. Now I'm going to give you one example, actually examples of the two searching algorithms to kind of explain how big O notation works. So big O is essentially a way of ranking the efficiency of an algorithm, how much space and time an algorithm takes as the input grows. So if I were to find the word pasta in this, well, how would you go about it? You would look through every single element and until you find pasta. And this took 16 steps to find pasta in a list of 26 elements. And because there's n number of items, which is there are 26 items, it's going to take you O of n. It's going to cost you O of n. And by that I mean as n grows, this number, the complexity of it is also going to grow linearly with the size of the array. So if you were to search for zucchini, for example, it's going to take you 26 steps. But if there were like zucchinis, let's take an example of zucchini being at the end of the list, and if there's 1,000 elements, it's going to take 1,000 steps to find zucchini. So how do we optimize this? What if we thought of it as, say, how you find a word in a dictionary, right? What if, like, you're searching for a word, say pasta in this, but if in a dictionary you would cut it in, open a dictionary from the middle, you would break it, and then you would see, oh, should pasta be in the next pages or in the previous pages, right? So you open a dictionary from the middle. Same in this case, you would break it up in half. And we know that pasta is going to be in the second half itself. So if I broke this array, the first path can be discarded. 13 elements can be discarded, and pasta is going to be in the second half. So now let's look at this array. We've significantly reduced our search space right here. And here again, I'm going to split it up again. And the first half is gone again because we know, sorry, the second half is gone because we know the pasta is in the first half. And we split it again, and pasta is going to be in the second half. And it took only 5 steps to find pasta in this array. So what's the complexity now? Because it only took 5 steps with this algorithm to find pasta. So this is called binary search because it uses divide and conquer. So for 26 elements, we needed only 5 steps. And if you do the math, it's log base 226, which is 5 steps. So the complexity is going to grow O log of n. And if you graph it all out, this is what it looks like. You see that the number of operations does not grow as much with O of log n, versus with O of n, it grows linearly. Any questions so far about big O? I know most of you guys knew it, but we did for some people. All right, over to you, man.
Let's give a hand for Anane. That was a lot of information. That was a whole course in like 10 minutes. Y'all have no idea. But yes, that was every data structure and algorithm ever right there. There's no more. That's all of them. We got them.
Okay.
Yes, data structures and algorithms. What is that? What is this?
Just camera, bro. You're live.
Oh, okay. Oh, I'm live apparently. All right, I didn't know that. This is a bigger crowd than I expected. Yeah, so I kind of have like a unique approach to teaching this. I think there's a problem with computer science, which is we've like kind of arbitrarily separated and divided. I don't want to stand in front of this thing. I'm gonna walk around.
Okay.
We've like arbitrarily like separated data structures into like their own class. Like, oh, these are trees, these are graphs, these are tree questions, or these are array questions. But the truth is, most of computer science is so interconnected, and so these like differences are that. It's just completely arbitrary. And so I wanted to take a novel approach here, and I've never done this, so if it fails, then thank you guys for showing me that it does not work. But otherwise, this will go great. I want to teach data structures and algorithms through this like mindset of problem solving, which is like the heart of computer science. And we're gonna do it through an example, so we'll get started soon. But before that, I thought maybe I could kind of just gauge the audience. Like, what do you guys know about data structures and algorithms? Anyone wanna say a thing? None of you know a single thing about data structures and algorithms? Yes.
Depending on like the algorithm and data structure, some works better with some algorithms are like more efficient for some data structures, like simplify.
Efficient. What does efficient mean? What do you mean by that?
Takes less steps.
Less steps. Okay. So would something that takes like twice as much steps be more efficient than something that takes like n steps? Interesting. Okay, that's an idea. Yeah, that's definitely one thing to consider. Go ahead.
I mean, the way I approach it, you have to get from one place to another place, and data structures and algorithms are like different routes you can take. Data structure is basically how you can store stuff and the information that you have, and algorithms, data structures are like the roads, and algorithms are the routes you can take to get there.
Okay, yeah, that's a thought.
Organizing it.
That's a thought. Why are you guys interested in it? Maybe I'll ask that. You guys can be honest. Sure, go ahead.
The only reason I'm researching or reviewing, learning about data structures is so I can like make the best code that people will like actually pay for.
Wow, this guy's passionate. Okay, I love that. Let's go.
Trent, I have an answer.
Yes, on
What is
your answer?
to avoid the tech interviews, and I'll just ask for a systems design interview because I don't like any of this shit.
Yes, that is the honest
Okay, who's
answer.
here to just pass interviews? Who don't care about this? Raise of hands. Okay.
Well, I'm glad you showed up today because
Yeah.
that's exactly what I want to talk about. Passing coding interviews. That is
Yeah.
a lot of people's kryptonite apparently, and I don't quite understand it. I think there's like this kind of culture of preparing for coding interviews, and it's very like misguided and very confused. What people do nowadays is they spam leak code questions, which first of all, kind of a waste of time, and second of all, it doesn't really like it's not an efficient way to study. Like, do any of you guys know people who are those kids who like, oh, they kind of just get it and they do like 20 questions and then they can just kind of get into like top companies? Anyone know something like that? Yeah. Well, a lot of those kids exist, and I have some friends who, like I have a friend who got into Citadel, did like 30 questions, made like 400K new grad and stuff. Last summer, I got offers from Google, Facebook, DoorDash, and Amazon, and I don't really do much lead code. And so the difference between people who like, bang their head against the computer doing lead code versus people who just get it is kind of like the methodology in studying. Because the truth is, when you like do so many lead code questions, it's kind of just like you're trying to almost memorize or trying to, in the background, remember these questions such that, oh, if that exact question comes up, I'll be prepared. But that's not the point. The point is learning how to problem solve. And there's only really like 20 types of questions once you kind of get to the heart of problem solving. So I hope to sell you on that today. I hope to make that case. Cool, that is an iPad. Let's
Yeah.
get started. All right, I
Yeah.
don't really use iPads, but let's
Yeah,
do
he
this.
took me to like Wexler Hall, which is like the shittiest hall in my opinion.
Yes,
And
yeah.
Yeah, he wanted the fucking chalkboard, and I said no, that's too primitive.
So I'm a math major, and we're pretty big on chalkboards, but this will have to do, huh? Damn, you guys are quiet. CS majors, huh? No interaction here.
No interaction. But okay, by the way,
Yeah.
there's a special guest that's in the audience, and that I didn't know who was gonna show up. Khan is in the audience right
Khan Axoid?
there. Yeah, he's right there.
Yo, 2 Sigma boy. What's up? What's up? All right. Well, anyway, I'm gonna start with the problem. We're gonna work through it together. I'm gonna hear some ideas. But if you've already seen this exact question and like you like have the solution memorized, like you don't have to shout it out and answer. Well, if you're like seeing it for like the first time, we'll kind of work through it. So imagine there's just a list of numbers. So I'll just kind of put random numbers here. And I hope that's legible. I want you guys to pretend that every number represents a house, and that is how much money is in that house. So it could be dollars or whatever unit. What is that noise? I don't feel safe, guys. Are we good here? I don't know. See, people are trying to break in and study like problem solving. That's how valuable this is. So you guys really take something away today. But anyway, a list of houses, and they all have money in it. The number represents the amount of money they have. And for you want to rob some houses because computer science didn't work out. It's a hard major. Robbing houses might be the easier approach. So you want to get as much money as possible. But there's a rule. That is really pissing me off. Oh my god, that noise. You
Yeah, I don't know
can't
where the
rob 2
fuck
houses
is that
in a row.
coming
That's
from.
the rule. You want to make as much money as you can, but you cannot rob 2 houses in a row. So, does anyone have any ideas on how they would approach this problem? not necessarily how you would solve this problem, but like how would you approach it? Like what would be kind of your first step in thinking about it? Yes, sir, from blue.
One approach I would think of is first.
You can speak up a little bit.
Oh, my first idea is to go through the entire list and find the biggest value, and then you find the next biggest. Then you go through the list again and find the next biggest value that isn't next to the first biggest value, and those two are the toughest.
That is a idea. Sure.
Another idea I have personally is if you're
Oh
able
my
to sort
fuck.
the houses, I know in this scenario you're not actually able to move houses, but if you're able to sort the houses from least to greatest, and then just access the last two elements or the last two houses in this scenario, you'd be able to determine what two houses have the greatest values and which houses in there. Or you could figure out, you could remove all the houses with values that are least.
Those are some ideas. Sure, I'm gonna just do a couple more.
Before I give my solution,
Just a little bit louder.
Before I give like a possible solution, for the house locations, are those like movable or not movable?
No, when you go into a neighborhood, typically you can't rearrange the neighborhood.
Okay. In that case, then what I was thinking about doing is you just find that you just look through the array with like linear search or something, and the runtime's probably not that great. It's okay, it's not that long. And then you would probably just kind of see which one's the largest, and then find what collectively on the sides of it the values are. So that way you're maximizing the space. If you're trying to rob a house.
This guy.
So if there's a value that's like really close to a higher value on the left side or the right side, you could rob that house and then the one to the right or the left, based on how much higher it is compared to the other houses.
Okay, that's an idea. Last one. Yeah, you.
Basically, we could do like, we can actually kind of see what we can go step by step. So, like for example, we are at house 3, so the max we currently have is 3. So when we move forward to house 2, basically when we move forward, we will see that either we have to move, basically since we can either skip over to the next house or we have to go step by step, kind of like a 3D problem. So we can either see whether we are going to take the
Yeah, I see where you're going. That's the right idea. Thank you. Okay, so well, basically these are some approaches. These are a lot of approaches. When you see a problem, there's two things that matter here, right? There is two things to consider. There is correctness, and that is obviously the priority. It always has to be correct. And then the second thing to think about is the efficiency. Now a lot of the algorithms I've heard, they're ideas, but I'm curious to know how you guys would try to like prove that it's actually correct, and then kind of going through that line of thought. Would it lead to something that would just become an exhaustive search? So when I say exhaustive, I'm referring to exponential searches, so like true to the end. That's like the worst case. This is kind of what I want to talk about. I think when approached with a problem, kind of like when I asked you guys, how would you guys approach this? None of you actually answered that question. You guys kind of answered how you would solve this, but I asked how would you approach it. It's a subtle difference, right? And that's kind of what I want to talk about today. Kind of like the art of approaching problems, or at least adding structure to that. I would say that a common problem I see with people who are studying for coding interviews is this like impatience to get into coding or start the coding, or even to start just solving that's way better. I love that, by the way, the light's on. This is great. The impatience to start coding or to start, solving the question or to jump right in.
Is that better?
I think the middle was perfect.
The middle was perfect. You just want to take pictures,
Yeah.
so.
Actually, can we have the lights so that no two adjacent lights would.
There we go. Write a Python program for that.
This is good. This is good. All right, guys, stop. Give me the T-shirt.
No, turn these off.
Go back to what it was.
Yeah.
2 steps ago.
Oh my God.
Okay, that's perfect. Don't move.
Okay.
Stop.
Yeah, perfect.
Yes, perfect. Great. Cool. Anyway, so I kind of wanna. This is so just money. All right. Anyway, so here's what I'm gonna do today. I am gonna give you guys a approach to solving problems. This is not how to solve. I mean, it is how to solve this problem, but it's a lot more than that. It's just a general structured approach to solving problems in general. We're gonna start with this as an example, and this is an array question, and more specifically, it's like a dynamic programming question. If you guys know that term, if not, it's fine. But I'm going to show afterwards how tree questions, graph questions, honestly, most types of questions can be solved using this exact same approach. So this like difference between graph questions and array questions is really arbitrary when you get to the heart of problem solving. So yeah, you guys ready? You guys wanna get into it? Pizza, exciting? All right, cool. Oh, Apple Pencil. Okay, does anyone know an algorithm? Oh, never mind, I found it. An algorithm to find the Apple Pencil. Anyway, so here's what I wanna say. When you're given an entire problem, it's a lot to think about, and it's pretty overwhelming to find the answer to the entire problem, right? Because so many things could happen, right? Because technically, when you kind of think of some ideas, you know, like, oh, maybe I'll check every other house because I can't get adjacent houses. Well, there's the case where what if the optimal path is actually skipping both of these houses and going from this to that, right? Because that could happen. In this case, you don't want to take the 2. Hold on. You don't want to take the 2 because if you do, you can't take the 3. But then you also don't want to take the 5 because if you do, then you can't take the 8, right? So there's just so many different things, right? And it's just so overwhelming. You have these ideas, you don't know if they're correct, let alone even optimal. So I would say kind of, you know, drop the optimal thing for a second and just focus on correctness. So here's the strategy. Step 1, pick an arbitrary point, or don't pick one. Assume you have an arbitrary point. So if this is an array, we'll call it, If this is an array, we will call it A. And these, chalkboards are so superior technology. Well, anyways, these are indexes. When I say an arbitrary point, I mean assume that you have some point somewhere in the array, call that A of I. Or actually, maybe I'll write out the steps so you guys can get something from this. So I'll say pick arbitrary point. Sorry, I have to go through this fast, so it's going to be kind of messy, but you know what I'm trying to say. So in this case, it's going to be A of I. Now, it's very important that you don't know what I is. I could be, you know, it could be 1, or it could be like 3 or 4. It could be anywhere in between. You don't know what it is. All you know is just some point somewhere in the array. You have that. Now, what I want you guys to focus on is, given that, how would you construct the best decision for robbing that house, or the most money you can rob once you get to the ith house? So like ITH, the ith house. How would you solve that, given the assumption that the solution in general is solved for every other I? So that was a mouthful. That probably made no sense, but I'm gonna build on that. So let's say we have a helper function called best, and it will return the best, or the most you can get from robbing the ith house. So just assume that you already have that function. So I'll just say A of x, and it's gonna return the best you can get for the A of x thing. So if you have that and you want to define it for the case where it's A of I, where that's arbitrary, given that you already have this solved for every other x, how would you define that? So that was probably confusing, so we'll kind of build the intuition here. That's the goal. Does anyone have any idea what I'm talking about? Does that make any sense at all? Yeah, so I'll kind of point at this and maybe it'll make more sense. So what I'm trying to say is, for example, if the arbitrary element happens to be here, if we know the best or the most money we can get from robbing every house up until I minus 1, and also I plus 1, whatever we want, if we had access to that information, could we find the best for the ith house, in this case which is the 8, like using only that information, so in like a recursive way? Is that enough to define what decision we should make at this point, whether to rob the house or to not? Anyone? Any ideas? What are you guys confused on? Is it like this house thing specifically, or is it just the idea of defining this arbitrary thing? Do you guys know what arbitrary means, or in this context?
Random.
Random, kind of. But instead of random, I would say, like, which part of the array it is irrelevant. Like, it can be any of it. Damn, he's leading us on that. Wow. He was not a fan of my response. Okay. Does anyone else wanna kind of say a thing? Anything? Sir?
So I feel like for this arbitrary I, you can either decide to rob it or not, right?
Yes,
And
those are the
making
only
that
two options.
decision influences what prior houses you could have robbed. So if you have information on the best amount of money you can make for the prior houses, you can just check which one is better, like do you rob or not. If you rob, you can't rob the prior house. If you do rob, you don't rob, then you can rob the prior
Okay, so
house.
that guy's a genius actually, so it is a little bit cheating. But yeah, what he's basically saying is, if you're trying to solve, like, imagine the array didn't even exist. Imagine it just ended here. If you want to find the greatest, the most you can rob at this point, and you have information about the greatest you can rob at this point and every point before it, is that enough to get this last final step? It is, right? Yes.
I don't understand that, because if you know that, like, let's say the value that you're arbitrarily choosing is the one at 8, right? So.
Well, you don't choose it, it's arbitrary.
Yeah,
Well,
so
as an example, let's say it was,
As
yeah.
an example, let's say it was I equals 3. If you know information about the best case scenario from I equals 2, why is that relevant for I equals 3 if by choosing I equals 3 you don't get to choose I equals 2?
What a great question. Yes, you guys hear that? He's saying, why is it relevant? So in this case with the 8, why is the information for the best at this point relevant? If you pick this, you won't be able to pick this. So we need more information. That's embarrassing. We need more information than just the last house. Is there any amount of information, the smallest amount of more information than just the best up until I-1 that would give you this? Just one more step. I'm gonna give it to you guys in the first one, and then afterwards I think maybe there'll be an intuition here. If we use the best at I-1 and I-2, in combination, we can use that to define the best for any arbitrary A of I. Do you guys see that, or want to know why? Because if you pick the 8, you can't necessarily use the best that's at this point. Maybe you can, maybe you can't, but whatever is the best up until this point, you can definitely combine that with the 8 and pick that. That'll always work. Whereas at this point, the best at this point could also not include choosing that, but you wouldn't know for sure. And so the reason you need both of them and not just the one that's 2 points before is because there's also cases where you choose not to pick the 8. You just kind of stick with whatever was the best of this. So this thing that I'm asking here with this question mark, it's just one line, and it is using the max function. So I don't know, we'll just say Python or something. The max between what? What two things? Yes. Yes.
Okay, I had to answer the question. So the
Question first, yeah.
I can answer.
Oh, okay.
The answer is the max between either choosing I-1 or I-2. Like whichever one, like either from index like -2 or index -1, if you know those two things, you should start from that and add the value that you add the 8 that you're currently arbitrarily choosing.
Yeah, well, it wouldn't be the best from I-1 or I-2 because this always increases. So if you imagine this like best thing exists, so we'll just say it's like blue, right? So I'll kind of like, maybe this will help a lot. I'll give you an example of what this would look like. So the best of this is 3. The best of this is still 3 because you could just not rob the 2 because you already took the 3. The best at this point would be 8. At this point where we get to the 8, the best would be 11. And then at this point, we can choose to take this 2, combine it with the 8 from the 5, that'd be 10. Or we can just stick with the 11. I think I'll do that. And at this point, it would be 12. So that's kind of what the best would look like if it was solved all the way through. But at this point, we're assuming it's only solved up into a certain point. Everything before, well, I guess it's solved for everything else, but we only care about the parts before I. what are you guys confused about when it comes to like this definition or creating this function? Does the word recursion help if I use that, like thinking recursively? Yeah. Okay, because I'm a math major. I don't say recursion.
I'm bad at discrete.
You're what?
I'm bad at discrete.
You're bad at discrete math. That's another thing I kind of want to say. Data structures and algorithms is just discrete math.
Exactly.
Like people like kind of blow off discrete math and it's like, oh, this is useless. And then like weeks later, they're like, I want to get into Google, and it's like, I don't know, like, do you like it? Do you hate it? Like this bridge it's a weird thing. Okay, well I guess I'll move on and kind of just state this. Maybe this will make more sense. If I is arbitrary and we have this best function, then the best at any given a of I would be the max between the best of I minus 1 or a of I plus the best I minus 2. Is that legible?
Is that English?
Oh my god. Yes. Yes. So we have this one statement that for any random arbitrary a of I, we know that the best up until that a of I is the max between the best of the I right before it or a of I plus best of I minus 2. Does that make sense?
Yeah.
Yes? Okay, nice. We're making some sense here. Great, so we have this, but that doesn't exactly solve the problem, because the problem's a lot bigger than that, right? It's not just one random arbitrary point where we get to assume the question's already solved. So how do we go from this to something, that actually solves the original question? Well, before that, I kind of want to say one last thing. Kind of just want to formalize this discovery we have. That the discovery is, if we know the best of I minus 1 and best of I minus 2, then we know the best of I. So that's the first thing. If we have just those two pieces of information, we know the best of I. Now, taking a step back from this arbitrary case, I want to move on to a simpler thing, which is what I call the trivial case. I think maybe as CS majors, you guys like the word base case. Is that what recursion? Yeah, there we go. The base case, the trivial case, the version of this question that would be so easy to answer that, really anyone could do it, right? If this was an array of size 1, obviously the max you can rob is just that one house, right? Does that make sense? That's an easy, approachable problem. And if it was an array of size 2, it would just be the max between those two houses. You can't rob both, you have to choose one. So just the max between those two, right? Very easy, very approachable. Now, I want to make the argument that these two, both very approachable, easy things, in combination, guarantees that you solve the entire problem. So let me kind of just write out the base case stuff. So we would say that the best of 0 is equal to array of 0. Best of 1 is equal to the max. Nice.
Messed up a little bit.
The max between array of 0, array of 1. We're back. Okay. Well, sure. So now we know two things. We know that we've defined the best of the arbitrary case. Yes. And we've defined the best of the two base cases. Now, I kind of want to take a step back from this and maybe develop an intuition here. Have you guys ever gotten like an 89.99 on a class and then she just didn't round? You guys have that happen? Kind of annoying, right? Well, what arguments does the professor make in that case? The one I heard. Yes, go ahead. I want to hear.
To say if they round yours up, they go on to round 89.99.
Uh-huh.
The next 89.
Exactly, right? If so 90 is an A, and then 89.99 is 0.01 away. So if you're making the argument that 0.01 isn't enough to go from an A to a B because it's too close, okay, sure. So then 89.99 is an A. But then since 0.01 isn't enough to change that, 89.98 is an A, and 89.97. And you can kind of follow that argument by induction until 30% is an A. That is the conclusion. If you follow that, like any number, like negative numbers are an A, if you keep following that. So kind of, on the same breath as that, if the base case, 0 and 1, is kind of solved, and we know that, and we know that if the last two cases are solved, then we know the next one, then by that same logic, then we'd also know the one after I, and the one after the one after I, right? And so this follows to the entire array. And the question is, the max amongst this neighborhood of houses, this array. But really, what you're thinking about is the max when the index is the last one, right? So A of n in this case, because n is the last, right? And so to know A of n, if we know A of n minus 1 and n minus 2, then we know that. But then if you kind of follow them backwards in the same direction, it just comes back to these two base cases. So when it comes to writing the code, maybe this is what you guys are interested in. When it comes to writing the code, I mean, so far we've just done the math, but writing the code is really just writing the math in code. I mean, it's the exact same thing, right? This is the idea, that's the important part. I can kind of write the code, I'll maybe kind of rush through some pseudocode. So if this would be define Rob houses. Let's say it takes in an array. Yeah, I would just, so if we let n equal to the length of the array, I guess minus 1, and then we would just return the best of n. And then to define the best function, let's say it takes in the array, so just imagine I passed in the array, guys. And then it's going to take in some I. And the two base cases, if I is equal to 0. I mean, I'm kind of honestly just going to copy and paste this stuff here. Actually, I'll write the first part. I'll write this. So in this case, it would be return A of I. Else, if it's equal to 1, bam. Otherwise, it is this great little thing that we worked so hard on here. Right, do you guys see how the code just immediately follows from what we just did? Bam, this is a correct solution. This solves the problem. And I don't know, I felt like breaking it down into these two little steps makes it a lot easier to understand large problems. As for being optimal, I will add one thing here. So it's possible that we would see the same, we would compute the same stuff over and over. If we're on the 11th, if we're calling the best for this and that, but then on the 8th we already called it for the 3, or whatever this index is, I guess 1. So to kind of optimize on that, we would just use a hash map. There we go, that's data structures and algorithms. I'm on topic here now, guys, see? I'm not gonna spend too much time on it, but I will say that dynamic programming is...
Before you go ahead, does anyone have any questions? Before we go ahead. Cool. Does everyone know what a hash map is? No. Okay.
Okay, I will explain in a second.
Cool.
look, that's probably not correct. I mean, the logic is there, but the syntax, we'll worry about that when we get there, right? Okay, so a hash map. I'm not gonna really explain like the behind the hood stuff and how it works, but just know this: a hash map is this constant time lookup table. So if you have, like let's say you have a list of things that you've seen today, right? So let's say you write a chair and a cat and a dog, and then you see a dog again, and you wonder, wait, did I already see a dog today? If it's an array, you're kind of going through that list. I saw a cat today. I saw a chair today. Oh, I did see a dog today. And it just takes like the list. The list would be like the length of the size of things you've seen today, and you have to search through it. And I mean, I already talked about searching. So you guys are
Let me give that a
experts.
try. Okay. Does everyone remember the pasta example? Hash map is going to allow you to find that in O of 1. Just O of 1. No O of n, no O log n. It's just going to allow you to find it in O of 1. It's because of the way hash maps store data. They store what's called a digest or a hash of the data itself, which allows it to look up that thing in memory in O of 1. So in that past example, we saw O log of n, O of log n. If you put it in a hash map, it's going to allow you to find it in O of 1. So yeah, there we go.
That sounded more mathy than anything I've said, to be honest. So yeah. So then basically same thing, right? Like you get to check if you've already seen it in constant time. You don't have to go through the list. So it's a tool that you use a lot in a lot of different types of questions, most questions, honestly. In this case, if we've already done a computation, for some index, then we would kind of go back and save it. So somewhere, before you return it, I would say save the results. Add that in your head, that line. And then we won't be like, doing repeated computations. And so now, not only is this a correct algorithm, it is the optimal algorithm. I mean, you could do it in a bottom-up approach with dynamic programming, but that really is just the inverse of like recursion with memoization. Those are big words, you don't have to know what they mean. But basically, now the argument I want to make is this exact approach that we used here for this one array question, which is step 1, find the solution to the arbitrary case, assuming that you already have the problem solved for any other case. And step 2, just think about the trivial cases. And in combination, you can solve the problem, a lot of problems. And sometimes you can't solve a problem doing that, but that gives you very valuable insight also. It should be like, oh, well, I guess this is an exponential, algorithm. So it's a very quick way to get to that understanding. So what I'm going to do here is I'm going to introduce some concepts. Let's start with the concept of a graph. It's not like the graphs that you kind of remember from high school. A graph is kind of just, honestly, it's just a bunch of circles and lines connecting them. They can really, there's so many types of graph, they can connect in any way. I'll say one way you can kind of visualize how this is useful at the least is kind of think about Google Maps a little bit maybe. Let's say you had some app and it was tracking the shortest distance to McDonald's locations, right? So let's say there's a McDonald's location, or just fast food. So let's say there's a McD over here. Let's say there's a Burger King over here, a Wendy's, my personal favorite, Cane's. And let's say you're at McDonald's right now, but you kind of don't want to be there. The vibe's weird. You heard some good stuff about Cane's, right? So you want to get to Cane's, but you're on a time crunch. You want to get there as fast as possible. But there's multiple ways. Look, you can go through Burger King, or you can go through Wendy's. These lines connecting them, you can think of them as roads or streets. Now, they all have a weight. What that weight means up for interpretation. It could mean how long the road is. It could just mean how bad the traffic there is or how long it takes to go through them. So I'm just putting some random numbers here at this point. All right, sure. So that's what a graph is. It's just kind of circles and lines connecting them. And it has many uses. One of which is sometimes a specific type of graph is a binary tree. You guys probably know that, right? That's freshman material, yeah? All right. Yeah. So maybe a graph wasn't taught to you as a tree, but what is a tree? It is, by my definition, circles and lines. right? And it's a type of graph. More specifically, a tree is it's a cyclic connected graph, but you don't have to think about that. There are lots of tree questions, binary tree questions. Sometimes trees have more than just 2 children. This is no longer a binary tree. Binary means 2. Trees can have multiple children. So when it comes to graph questions and tree questions, technically, if you kind of know how to solve graph questions, that's the more generalized data structure, right? Everything that is true about graphs is, by definition, also true about trees, because trees are a type of graph. So I think this is one of the biggest disconnects in computer science is the world of graphs. So linked list, another type of graph. So like the world of nodes and graphs and trees, and the world of arrays or dynamic programming and greedy. But the truth is, those 2 things are also very connected. I mean, I think probably every dynamic programming question in some way can be represented as a graph and solved in the same way. I'm going to give you guys some questions to play around with. I'll maybe walk around. And so here's the I guess the goal here. I'll start with the tree question. It's a little bit easier. So let's say you're given a tree, and in this case it will be a binary tree. And you want to find the shortest, or not the shortest. You want to find the least weighted path to a leaf. So a leaf means it's just like these last. Oops. It's just these like last little things here. So this is a leaf. That's a leaf. That's a leaf. That's a leaf. It means it has no children. That's what being a leaf means. You start at the root, so you're given the root, and they all have weights. So I'll just once again put random numbers here. You want to find the least weighted path to a leaf. So let's just say it costs money to visit. It costs money to visit a node, and you want to get to a leaf, but you don't want to spend too much money. So in this case, I would say that solving it is very, very similar to the approach that we just did for that array question, where if you just kind of think about the arbitrary case, and the base case, which hint, being a leaf is kind of a trivial question if the path to a leaf is a question, right? Just being a leaf is pretty easy, right? But if you're not a leaf, if you're arbitrary, which I would never say someone is arbitrary, right? That's a very mean thing to say. But in computer science, we get to say that about nodes because they don't have feelings. So some arbitrary node, how would you kind of define what the best path there would be in terms of its children, and assuming that we already kind of know the answer or the problem's already solved for its children? On that same breath, I think we can also kind of do the same thing for this graph question. Let's say you want to find the shortest path to Keynes. Don't worry about these numbers. These numbers are subject to change. So don't like hard code any of these numbers. But let's say you're given some place that's not Keynes. It could be Wendy's, it could be BK, McDonald's, I don't know, you're just given some node, and you want to find the shortest path to Keynes. Could you do those 2 steps that I described in the last example of defining the arbitrary case and the base case? And if you guys can, maybe you can move on to the code. I'm probably gonna, once again, the code is really just immediately follows the thing. So yes, do you guys want to get started? Do you guys have paper? I don't know, is this a thing? What?
They're supposed to have laptops. Last I checked, CS majors carry laptops, but
Yeah, I guess it's more of a paper problem.
does everyone have their laptop on them? I don't see any laptops here. But I'll take a minute to show you some code on screen just to kind of give you an idea how it's represented. And you don't have to note this down. This is pretty simple. Let's just first off, I wanted to show what a hash map looks like. And so a regular array looks like this, but a hash map, when you're trying to find an element in O of 1, what you're gonna do, key value pairs. And if you ever wanna find a key, it can do that in O of 1. And that's what you use to your advantage. What you can do is, I can take this array, write a loop, and convert it into a hash map. So if I wanna access that 10 times, I can do that in O of 1. And so right over here,
if I do a
Turn if the element exists or not. So if I do eggs here, it's going to return true, which is what I have here as the value. Or what I can do, I can also use hash maps to track count of how many items of that I have. So for example, if I have 6 eggs, 5 bread, and 4 milk, say. So if I run this again, it's going to output 6. But I can just, add a random value here, and it's going to say not found. So this operation itself was done in O of space. So there's one, so again, twice, and hash maps themselves, that's the trade-off you're making for that extra speed you're getting. As for graphs, this is how they're represented as an array. Basically, vertex 0, this is index 0, so vertex 0 is connected to vertices 1 and 3. Vertex 1 is connected to 0 and 2, 1 and 3, 0 and 2. And this is how the graph itself would look like, and this is how it's represented in an array. I know you don't like computer science.
Major now. I don't know if that was obvious from the conversion therapy that I'm trying to get going on here. Switch to the math side. Weapons of math destruction. It's going to be a thing. We're starting a cult. On that note of the way that graphs are represented, I will say this. The way that things are represented in code, or the coding element of something, is honestly kind of, like, most of the time kind of trivial once you kind of know what to do. Like what is an algorithm, if you really think about it? Like, do algorithms exist within the context of coding? No, right? The algorithm to being hygienic, right? There's an algorithm for everything. It's a thing that exists as a concept. And the moment that you kind of instantiate, right? It's not the Spanish that's important here. And if you want to be better at poetry, you don't get better at Spanish. You get better at the abstract concepts, right? And so this like focus on the coding, obviously if you don't know how to speak the language, yes, you do need to learn how to code. That's a true thing. But the coding is only just representing the ideas that you actually have and how to solve the problem, right? So this is where most of the focus is. And so how to represent a graph, over code, it's important, and I trust that you guys will learn when it's time. But knowing how graphs operate and how to think about them, it's just a much more valuable, thing to worry about. And I would also argue it saves you a lot of time because in the context of coding interviews, what people are doing nowadays with all these problems and pattern recognizing, quote unquote, to me it kind of feels like if you're being tested on a movie and then you try to study for the movie by like learning trivia about the movie, right? And it's like at some point just watch the movie. Like faking it is harder than just getting good at it. And that's where we're at. And the culture of CS is kind of just learning a lot of trivia, problem solving. And I'm gonna go to the tree example first. It's a little bit easier. But the cheapest way to get to a leaf. Does anyone want to kind of come up here and draw the relations or the arbitrary case, or just kind of talk about it? Anyone want to contribute? All right, I have not sold you guys on this at all. Okay. Well, does anyone want to say what the trivial case is? Does anyone like anything that I said today at all? Any part of it?
Be brutally honest. It's our first time hosting like a data structures thing, and we want to try to do something different than the school does.
Yeah.
So,
You guys liked it more?
you like it more? Okay, if you don't like it more, we've got samosas to make up for it. So, who wants free samosas?
Is
Raise
there
a
any
hand.
stand comedy? We have some time.
He is a professional stand-up comedian.
Not professional yet.
Getting there. Who wants samosas?
Okay, so what is the shortest path to get to the samosa? Does anyone want to talk about the arbitrary case or the trivial case?
Straight line, right up front.
Yeah,
Actually, I just gotta go up a little bit.
I don't know, maybe you kind of, there's like, yeah.
Okay.
See, we would have to compare the edge from this, the edge from right here, this node to that table versus the edge from right here to that vertex right here, which should be this, to right there. So that actually is more steps in terms of how many vertices you have to visit, because then you have to visit this one, a second one, and then eventually the final. Whereas in this, just one, two steps. However, we don't just care about how many vertices you visit. We care about the total weight. Yes, I hope that answers this question for you guys. Does that help?
Good
Nice.
one. All of
Nice.
YouTube saw that.
Oh, okay. All of who? All right. Nice. I guess I'll kind of talk about the philosophy of, like, have you guys ever heard the phrase divide and conquer? Do you guys hear that a lot?
Yeah.
What do you guys feel about that word? It feels kind of schooly to me. It just feels so academic, right? It's kind of a turn off, huh?
I
Yeah.
went over it if people
Oh,
were
did you?
listening. Yeah.
Yeah, no, everyone got everything you said, by the way. Everyone is, no, you went a little fast. I liked it. I love Monterey's presentation. I'm a big fan of his, actually. Anyway, yeah, so when it comes to divide and conquer, there are problems that can be solved by divide and conquer, and then there are actually problems that can't, where even if you had, the optimal substructures, you still can't even solve the arbitrary case. And so, the point that I'm making here is not, hey, guys, we can solve all questions by working on subproblems, but the point is, even if you can't solve a question by breaking it into these subproblems, that is the most valuable insight that you can get on that question. Because otherwise, you would be in a coding interview, just doing dynamic programming for 35 minutes, and at the complete end, you'd be like, oh, wait, this doesn't work. And it's like, yeah, you could have learned that in the first 2 minutes by just getting directly to the heart of the problem, right? I mean, you want to solve the problem anyway. You can do it indirectly, or you can do it directly. Think clearly. Okay. Yeah. What did you guys expect today? Kind of curious. What do you guys want to learn? And nobody wants to learn anything?
I
Yeah.
guess
Yeah.
I didn't expect any specific content, but
Mhm.
I expected this presentation pretty much to go like this. Not maybe as we're all kids, so whatever. I'll just kind of.
Yeah, you weren't here, but I did a show of hands, and when I said, wait, okay, let's do that again. Who's a freshman over here? See, everyone.
Oh wow.
See, I
That
told
would
you,
be helpful
man.
context actually.
Yeah.
I would have known. I would have done TikTok dances up here. We could have related on the algorithms. Well, I feel like I explained this in a way where you don't really have to have any CS knowledge to understand the concept of circles and lines, right, and how they connect. And I guess that's kind of the point that I'm making here. If you take anything away from me today, is that CS is just all circles and lines. So don't let anyone tell you that it's anything
Really?
more.
Where are the lines and circles in arrays?
In arrays? Kid, you have no idea. I can tell you right now. Well, anyway, yeah, I guess here's my goal. I hope some part of my voice is kind of implanted in the background of your subconscious, such that when you're presented a problem, you at least feel the urge to attempt it in a more direct or mathematical, gross word, right, way. Yeah, any questions? I guess it doesn't have to be about this in general. Any questions about anything ever?
So, when we're doing a question of
You can go a little bit. Oh.
yeah, so when we're doing questions or questions that can be solved recursively or using the divide and conquer approach, it's much easier to think about the methodology you used of finding a base case and then finding the arbitrary case and then linking them. Can you cover an example of a question which does not use recursion or which does not use the divide and conquer approach, but still show us how you would break down that problem into smaller categories and solve the sub-problem? I know it doesn't really make sense, but what I'm trying to say is, can you cover a question which doesn't necessarily fall into the bracket of recursion, but also solve that by breaking it down into certain steps?
Well, I mean, I think in some ways you're kind of contradicting yourself in this line of thought, right? I mean, okay, what is recursion? It's a thing in computer science, and you can define a function recursively. But if a problem can't be solved by dividing it into smaller problems, and then if you can't use the optimal subproblems to kind of arrive at your answer to your current problem, then it's just not really a divide and conquer problem, right? There are problems that definitely you can't do that. I can maybe give you an example of that, but on that note, I will say that problems of that nature are oftentimes, you know, like exponential. You guys don't know that word. They're oftentimes like, you have to do an exhaustive search, as in you just have to check every possible thing ever and record all of it and hope, and then you'll just kind of see which one did the best, right? It's a very inefficient way. And when you can't use optimal substructures, you know, in meaningful ways, that kind of is a clue that you might have to just do an exhaustive search. So backtracking problems, you guys will learn that word. But I will say a very large amount of questions, even if you aren't doing recursion, quote unquote, you can still break it into subproblems and solve it in ways like dynamic programming, which once again is recursion. And there are greedy algorithms, which basically just mean that you can, to be greedy means that you can solve the arbitrary case with no additional information about the best previous cases. That might not make sense now, but remember that, and then you're learning greedy. They're going to teach it to you in a not that clear way, and then just remember what I just said. It means the arbitrary case does not rely on the best version of the previous states of the array. Yes, greedy. What time is it? Can someone yell at the time?
6:47. Okay, Trent. No, don't need the mic. Come over here for a second.
Oh, this is scary.
Yeah.
Am I getting fired?
Yeah. No. Pipped. So, constant, like,
No, I did not get scolded. I got some advice that maybe we can start with some easier problems and maybe more practical. Are you gonna open up LeetCode on it?
Yeah.
Yeah. So I guess on this final thing, we can kind of just end on a actual LeetCode question. It's gonna be a classic question. It's called 2-sum, and there's a harder version called 3-sum, and 4-sum, and by induction, for every n. And an arbitrary, no, I'm kidding. Guys, please keep saying arbitrary case for everything for the rest of your day. It's gonna build an intuition. This is math. I'm an educator, apparently, now. You know, I've become an educator.
Okay, how many people here have done this problem? Okay, is it okay if we go over this one? Yeah? Do I hear a good yes? Firm yes.
Okay, yes.
Do it. Write code.
Can I use a, what do I do? It's kind of hard to read the question, I'm assuming.
No, I can zoom in.
Yeah, just zoom in on the array. Or the question, well, whatever. Basically, you're just given a list of numbers and a target, and you want to find two numbers in the array that add up to the target.
Two numbers in the array that add up to the target. That's it. So if you've got 2, 7, 11, 15, you got to find only two indices of the two numbers that add up to the target.
Yes.
And this is going to be a good explanation of how to use hash maps.
For sure. That's kind of a hint or spoiler alert. But another thing I'll say about when the art of like approaching problems is like a lot of people are already probably thinking about code and hash map and a lot of stuff, but it might be helpful, you know, if you're stuck and you don't know like where to go, is how would you as a human solve that question? Like if you weren't writing an algorithm to solve it for you, if you were given this list, how would you find out if there are in fact, you know, two numbers that add up to that? Just as a human, right? Just going by hand, and can you, I guess, explain that in code? Because that's, once again, all coding is, right? Just explain anything. Yes?
I mean, the first thing at least I would do if I was a toddler is I would remove all the numbers equal to or greater than 9. So, because if the number's greater than 9, they can't add up to 9. Or if they're equal to 9, they can't add up to 9.
That's a good insight. Yeah, that is a true thing.
If I need two pairs, that's the first spot that can add up to 9 instantly.
Yeah, that's the question. Did you raise your hand? Anyone? Oh, good. Yes. That's true. Well, is the constraint of this problem that there's no negative numbers? Could you check? I think that might be the constraint.
Yeah. So.
Oh, there are? Wait, no. Wait, go on. Oh, yeah, you're right. Huh. Well, if it
It's
was
still
positive
doable.
numbers, yeah. I mean, I guess in the context of being a toddler, it does make sense because negative numbers, you don't see negative numbers, right? So still, good intuition, but yeah, I guess that does change it a little bit. So you can't rule anything out. As a human, okay, so you want to find two separate numbers. Like, how is your brain as a human, like, could you scroll a little bit on it, back to the example of the 9? Like, clearly there is an example here, or there is a solution here, the 2 and the 7, right? How did you guys kind of like keep track of both of those numbers, or what's like the intuition?
So at least then changing it up, I would take the first number, add it by the second number, see if that number is equivalent to 9. If not, I'll take the first number, add it by the third number, see if it's equivalent to 9. And I just keep going until it is.
Yes, exactly. 100%. Yeah. So if you kind of have like as a human being, you have 2 fingers, right? So if you kind of just like keep your finger on one number and then kind of keep okay. Like, right, you can kind of just go through it like that a little bit, and you will get to the right answer eventually, right? Like, it will check every pair of numbers. That will check if there is a target, right? Does that make sense to everyone, why that would solve the question?
Yeah.
However, if this list was massive, and I mean just like massive, I mean, your fingers would be doing that for a long time, right? Because it would be n squared. So just a list of 10, you have to do 100, you have to do that 100 times. If it was 100, it'd be 100 squared, right? It's just, it grows at an awful rate. So wouldn't it be nice, you know, if there was like a better way than having to check every possible pair? Instead of thinking of it in terms of hash maps already.
Yeah.
Yeah, go ahead.
So I'm gonna go over 2 examples, one without hash map and one with just.
Or just
one
write
with
what
just.
I just said. Yeah.
Yes.
Write the answer
Wait,
right
I didn't hear what you said, but like I have one n squared implementation and one using hash maps. And what we're gonna do is we're gonna run them with like a really large input. And we're gonna see how much time it takes between the 2 algorithms. So we're gonna put the horses to the test. So did you go over to like the n squared approach, or what did you go
Yeah,
over?
we were all having fun. We were talking about how we're gonna use 2 fingers and then we're gonna like, yeah, so in this example, your finger is a loop. Did you guys get that? Did you guys catch that? That's what kind of doing this means. It means iterating through a loop. And you have 2 fingers because, you know, you're keeping track of the first one, you're holding it there while you go through the rest, and then you kind of move on, and then do that again, right? So that is a double for loop solution. That is an n squared solution. Anne is currently coding that, allegedly. I don't see any code though, right?
Give me a sec.
Yeah, I'm just kidding. Anyway, yes, that is the first approach, and there is a better approach. For example, let's just say you had like a phenomenal memory, right? Like you're holding that 2, or you're holding that first pointer, you're kind of going through it with the second one. But if your memory was just like really good, and you came across, let's say at some point you came across a 5, and then you're like, wait, I've seen a 4 already. Then just that information enough would be enough to know that, you know, that would add up to 9. So you do have a pair, right? So if you can keep track of every number you've ever seen, and just your memory is good enough to just know, you know, immediately, like in constant, like in O of 1 time. I don't know if you think about your brain in terms of time complexities, but if your brain in O of 1 time can remember, oh yes, I know who that is, right? Like people, like, you know, think of a person, think of Steve. Bam, O of 1 time, you guys remember him, right? You guys don't have to search through every person you know. Just, there's like a special spot for Steve or Kamal or whoever, I don't know, I don't care, right? So when you go through the nums, it's the same thing. If you've seen a number that when added with the new number you've seen, if it adds up to the target, then you don't need to like fingers, right? You kind of just have to go through it once and just have a really good memory as you go through it, right? So that is what a hash map is. It is a really good memory, kind of, in this context at least, right? When you add something to a hash map, you can check if you've seen that in constant time. So in this case, if you were going through the target is 9, and you
Right.
see.
So what I'm just gonna go ahead and implement the n squared one. So let's loop through the first array the first time, right? And then we're gonna do that again. Do I need to make this big? So what's gonna happen is that for every single number, it's gonna. So if we're on 2, it's gonna go 2, 7, 11, 15. Then we're gonna go on 7. It's gonna again do 2, 7, 11, 15. And then whenever we run on 11, it's gonna do again 2, 7, 11, 15. So if I go ahead and I do, first off, one of the constraints is that you may not use the same element twice, so that's what we're checking for here. And I want num_i plus, it is nums_i plus nums_j equals target. Then I can just return I, j. Otherwise, I can always return empty element. And if I go ahead, let's bring up the console. If I run it, math majors may not laugh. Okay, so it got accepted, right? But these are very small inputs, right? This is like just 2 numbers, 3, 4. What if my input is something along the lines of this? I'm gonna copy paste this right here. Hopefully it works. So notice how big this list is? What's gonna happen if I do it now? These are 10,000 numbers. So guess how many operation? What?
Sorry, go ahead.
Yeah, it's good. Yeah, it's gonna set the servers on fire. But for this, in this case, guess how many steps we're making? Does anyone want? These are 10,000 numbers right here. How many comparisons are you making? Any guesses? Just give me. You can give me the mathematical formula how you got it. There you go. Okay, 10,000 squared.
20,000 squared? Because you're checking for you're doing 2 different comparisons if I is not j and if I is not j.
No.
That's not exactly how time complexities work. If you do 5n operations, so for every n you do 5 operations, versus for every n you do 10 operations, those are still both O of n.
Okay, but that doesn't tell me comparison.
So I'm just gonna run
Comparison's
this.
the old one thing.
Trent, I'm just gonna run this. Okay, nums has to be between. Okay. So I just need.
Are you?
No, I was gonna say like he didn't ask about complexity. He asked how many comparisons happen.
Yeah, so comparisons
Oh,
are good. I mean, how many steps? I mean, this is negligible comparison, to be fair.
Yeah, I
They're
think
all 01 comparisons, and there are 20,000.
Yeah, you're right. There are 20,000 comparisons. Yeah, I see.
Not that it increases complexity, it's just like mathematically more. You're just doing.
See, so I submitted that n squared comparison. I submitted that n squared solution. Do you see how I only beat 5% of the submissions? Because I've submitted one of the slowest algorithms. It took 8 seconds for that n squared algorithm to work. But just give me the mic. It took 8 seconds to perform those comparisons to basically solve the entire problem. But if I go ahead and do that again, and this time what I'm going to do is I'm going to have a hash map right here. So let's define like a hash map K. I'm just gonna keep this. You can have it back, man. I need both my hands to type. And you don't have to type, you're a math major.
The way he just uses me and throws me away when I'm not. You're for free, by the way. Sit out your business.
Okay. Okay, so in this loop right here, what we're doing is we're taking all of these numbers and we're making them the key of the hash map itself. So what's going to happen is, if you look at the old thing I had here, and I'm just going to open that up real quick. So K, if I print out K here, oh, does it not? Oh, where's the console? Does it not print out the fucking? Oh shit. Where's the? Oh. Man, lead code is something. Okay, so what's gonna happen is all these numbers that you see, 2, 7, 11, 15, right? This is index 0, 1, 2, 3, 4. The hash map itself is gonna represent them as 2, 2:0, 7:1, 11:2, and 15:3. And this is how it's going to be in K once we run this code. Once we run this loop right here, that's how it's going to be represented in K. And the advantage of that is if I know that one of these numbers is there, if I take 2, for example, I just need to search the thing for 7 right here, and that search is going to be O of 1. And let's try and run this when we have a large input. So once I have this, what I'm going to do is
Wait, one thing is quick. So the K for like saying the hash map is O1.
sorry, what?
So the saying of the hash map, that's O1.
Yeah. So putting it into the hash map is O of n.
So looking for like in the hash map itself is O1.
Yes. So it cuts down our number of operations by a lot.
So why are you doing 2 searches?
2 what?
2 searches.
2 searches? I mean, okay. Okay, let's try running this. Hopefully it works. Hopefully there's no more syntax errors. Okay. So for this one, what have I done here, right? Basically, I sorted, again, the numbers themselves as keys and the indexes as values. And what I'm going to do is I subtract the target from the current number I'm on. So if I'm looking at 2 right here, I subtract that number from the target itself. So I'm left with 7. And if 7 is in K, and that particular index in K does not equal I, because you cannot use 2 elements at the same time. You may not use the same element twice. You can just return those 2 particular indexes. So that's how it works. And if I go ahead and submit this, notice how I've beaten 69.70% of all the solutions, as opposed to my other submission, which only beat 5%. So notice how it took only 64 milliseconds to do this with a hash map versus 8 seconds to do it with n squared. On the other hand, the space that I took was more with the hash map. It was 0.3 megabytes more versus 15 megabytes with this one. Does that make sense why you should use hash maps? Does everyone get it? Any questions?
No, but isn't that basically like a dictionary in
That's a hash map. Yeah.
That's a hash map.
What is the more optimized version of it? Because it just needs 8%.
So-
13% of it.
So, I think for that we have people like Connexoid to do it, but yeah.
Another thing I think which I think you can point out is that just because it's the cohesive percentage of solution, the runtime given by LeetCode doesn't really matter that much. I mean, what's more important is how much it is taking theoretically. Like if it's a big O n, O log n, runtime, how much is taking from that.
Yeah. So what?
The coding interviews, they will check your theoretical runtime.
I mean, that last 30% is also kind of random.
I mean-
if we just hit it again, we might get 90%.
But like the theoretical runtime itself is O of n, right? So I hope that answers your question. 69%. Well, that also depends on how overloaded LeetCode servers are. So
yeah, it's not like necessarily.
yeah, this is good enough to secure the bag. If that's what you want to hear, you'll get 120K out of college if you do that.
Wait, 100K of college doing what?
This.
This exact thing.
Okay, whatever question they ask, just say the answer is a hash map, and you got it in the bag.
So like, say if you want to solve this, we just say it's a hash map, right?
I mean, something like this. I mean, to not every question, but like for most questions, if you use a hash map, you're basically good. Am I wrong or right?
I mean, I don't know. This is a different philosophy.
Okay.
But yes, a hash map is a very, very common part of. Like, it's not even like, oh, these are hash map algorithms or hash map problems, because a hash map is also just a stepping stone in like most LeetCode questions. Or
But weren't you asked in an interview, what would you do if you had a conflict with your manager and you said hash map?
Yeah, you gotta use it for behavioral questions. You gotta use it when you can, you know, it's very pretty cool. Where are we? This is good.
Yeah, it's 7 p.m. People have
Yeah.
a life. That's why they went.
Well,
thanks for sticking
I
around.
hope you guys
all of us.
enjoyed. I hope you guys learned something. We'll be here.
Yeah. Do you have anything else to explain?
Well, it's 7 p.m., so I'll be here eating pizza if you guys have
So are we doing the resume review stuff? I mean, I just want to take like 5 minutes to like talk about resumes and resume reviews. Most of this stuff is known, but I'm just still gonna go over it just in case there might be just one of the points that you want to consider. First things first. Don't lie on your resume. A lot of people do that. Sometimes it happens accidentally. Sometimes, like you took that intro to like MySQL course, and you put SQL in your resume. Don't do that. You have to. The ideal way. How do you decide when to put a skill on your resume, right? The way you do that is to demonstrate each skill through projects. Have you done a project that involves heavy amount of SQL? Have you taken a class that involves databases? That's when you put a skill. Because whatever skill you put in your resume, you're gonna be grilled on that, for sure. But if you cannot answer simple questions based on that skill, the company is gonna not hire you, and they're gonna be pissed. No grammatical errors. Very simple. If one of the recruiters are grammar Nazis, if they see a grammatical error, they're gonna call you out for it. So don't do that. It also shows if you yourself have read that resume. So don't have any grammatical errors. Use action verbs and mostly past tense. And action verbs are certain verbs that ASU gives you a list. Just look up ASU action verbs. These are the recommended words to use in your resume, so use them. And make sure your resume passes ATS, and ATS is Applicant Tracking System. And this system itself is basically a system that companies use to filter out resumes. These are basically like bots that look for certain keywords, and if your resume doesn't pass, if that robot cannot parse your resume, you're gonna get screened automatically by a robot. So that's about it. If anyone wants their resume reviewed, I'm gonna be coming around. And yeah, that's about it. Thanks, guys. And these are all the awesome people that got you the food, and yeah. Thanks for coming, y'all. And give it up for Trent Black, please. If you haven't subscribed, go subscribe to his YouTube channel. He's got one of the I'm not gonna lie. He's got one of the best videos on data structures and algorithms, which has more than 500,000 views, and it's only 15 minutes long. So, and it covers more basics than we covered here. So I would highly recommend go check out Trent Black's YouTube channel. Once again, thanks, guys. All right, thanks for joining us live.